So what I want to talk to you about today is how do you, as the engineers and the users of the system, actually use our product to bring your models into production and actually use them for real things. And so we'll talk about, right in this example, going from PyTorch to SambaFlow. So the goal, which you might have gotten from the previous discussions, is that we don't want you to have to totally rewrite everything you've written already. We want you to be able to take your code as it exists and bring it over simply and easily. So you bring in your model from PyTorch, and you'll mostly leave it as it is. It'll stay 99% Torch. You'll make a few tweaks to have it run and compile on RDU, and that's about it. So at the highest level, what you would first do is you would convert your Torch model, the compute graph, into a graph that can be compiled for SambaFlow. And we have a function for that, samba.fromTorch model. That will take your model parameters in your current Torch model and convert them into Samba tensors. And we'll go over what those are in a couple slides. And then once you have the model converted and compiled, well, then you can run it. And that's something that the Common App Driver helps with. Helps with things like compilation, performance, measuring, and running. So a Samba tensor is really just a wrapper around a Torch tensor with a few additions to help it work optimally on an RDU. So a Samba tensor, each one is named. This helps with tracking and tracing the tensor as it moves through the RDU and through your graph. And while optional, you can specify a batch dimension. By default, it's usually the 0th element of the tensor, but you can specify it if you have a different one. And the sort of the function you're familiar with on GPU to move from GPU memory to CPU and back and forth, we support those as well. So you'll see on the right side of this slide that we have a little list of commands. So .data, .batchdim, .dtype. Those will pull out the elements from the Torch tensor that's within the Samba tensor. And then we have special ones like SNName, which is the name of the Samba tensor, SNGrad, which is actually the gradient on RDU. We'll pull it out for you. And then .cpu and .rdu, those will transfer things back and forth between devices. And overall, a Samba tensor can be treated like a Torch tensor. So you can add, you can subtract, you can reshape it, as you would a typical Torch tensor. So I've mentioned before tracing. So what exactly is that tracing? Well, tracing, what it does is it walks through the model with what we call dummy tensors to form the graph. So what that is it's literally the stack walks through your graph to understand how it changes the shapes of its tensors so that it can effectively map onto RDU. As you saw previously, the RDU consists of PCUs, PMUs, switches, various pieces of other, like address generators and such. And since we are mapping your actual model onto that chip, we need to know specifically, how the data is manipulated, how the tensors change, so that we can, use only what's necessary on the RDU. This tracing can either be done automatically. So when you tell us to compile your model, we'll do that tracing for you. We'll just trace it right there. When you go to actually, say, run training on your model to actually train it to be useful, you can manually kickstart a trace via the trace graph function, and that will trace the graph to put it onto RDU. And the whole point of this tracing, as I mentioned, was so that the compiler has a full picture of your model, so that it can most optimally map your model onto the chip. So, how do we trace it? Well, the model definition, it remains in Torch. What defines it for us is the forward pass. So the forward pass determines, how you push data through, and the backward is just the opposite of that. So we only need the forward to define how things get mapped and traced. One thing to note here is that we don't currently support control flow in your model. So if your forward pass contains if statements, we'll only evaluate the portions of the graph that evaluate the true. So we highly recommend that you do not use control flow in your model definition to run on SambaNova. So as I mentioned earlier, to compile, you can use the common app driver, and to train, you would call tracegraph to actually trace the model onto RDU to train. Okay, I'd like to pause here. Are there any questions so far? Okay. So moving further into SambaFlow and how it works, you all might be familiar with the NumPy PyTorch functional overrides, wherein if you provide an input to a torch function and those inputs are NumPy arrays, Torch will pass through and call the NumPy function that works for those inputs. So you see, a graph here that works like that. Input comes in, is it a NumPy array? Yes, well then call the NumPy kernel on that. If it's not, then is there an array function defined for that input? If so, use the user API. And if none of those are true, well, error. This is a similar flow to what SambaFlow implements for PyTorch. In that when you give us, when you're using Samba tensors and you pass a Samba tensor into a torch function, SambaFlow will intercept that and actually call the appropriate SambaFlow function on that. So for example, here, you have two Samba tensors, A and B, and you want to add them. So that leads to a torch.add. And SambaFlow will recognize this and call Samba add on those. It'll do the inference on shape and type and generate a Samba tensor, and then that will be made as part of the full model graph. And that's all transparent. You don't have to actually specify those. You can just leave your torch.add where it is, and we'll intercept it. And the same for most functions in PyTorch. Okay. And now model parameters. So the actual structure of your graph from PyTorch. So operations, with weights, have internal parameters. For example, here, linear being an operation with weights will have various parameters associated with it, any given number. When you operate on that, when you call that from torch model, what will happen is that Samba will in place replace those with Samba tensors. So it'll trace through, and in the same spot in memory, it will transform all of those into Samba tensors for you. And those will be mapped as part of the graph. And again, this is something that's transparent. You just call the model conversion function, and we do all that for you. You don't have to manually do this. So synopsis of where we are so far. So you start with your PyTorch model, right? Just pure PyTorch. You will convert your parameters to Samba, via the from torch model. You will convert your tensors to Samba tensors with a call to from torch tensor. When you're doing your tracing, you pass in the Samba tensors, and you can compile and run via the common app driver and tracegraph. Right, so that's where we are right now. And this is, a broader picture. So we're going to look into a little code example just to see what that looks like. So for us, when we say run, we mean train. And that is a two-step process. The first is compilation, because you need to compile them all to run on RDU. That's what that PEF is for. And then you can call training on that PEF. That will give you an actual model that can be used. So to begin with that compile, you need to pass in the model inputs, and an optimizer for compiling and tracing. And your training loop will stay mostly the same. Whatever that was, you'll leave it as it is. And on the right here, you'll see input definition, right? So image equals samba.randend, and then batch size, num features, right? This will generate a Samba tensor for you. When it comes to the initial trace, when you're compiling and you're mapping for running, the data in the tensor does not matter. What matters is the shape. In order to fully map your graph, your model onto chip, SambaFlow needs to understand how your graph will change the shapes of your tensors. It doesn't really matter the data inside of it. So it can be just random or zeros or all ones. But again, just what matters most about the inputs is the shape when it comes to tracing. Then you'll see that we have the model definition, and the model is a resFFN logreg in this case, right? Something simple, standard from PyTorch. To convert it over, from torch model underscore. That will take your model, convert it in place. So it's the same model in the same place. It's just that now all the parameters are Samba tensors now. You define your optimizer, and out of the box, SambaFlow supports SGD and AtomW, but you can provide your own. You can define your own. That's fine. And then a simple if-then statement. So if you pass in the run command at the command line, well, as I said, you trace graph first. Then you'll call your train function, and that train function will, what you have will be from what you have from PyTorch, but most likely. And otherwise, you can use the common driver to do things like compile. And you'll pass in your model, your input, your optimizers, what have you, and that will handle all of the details for you. And what you'll get out of that is the results, either a PEF, maybe you did measure performance. So again, we want this to be as easy to use as possible, right? We don't want to add too much overhead to your already complicated work, right? Models aren't easy anyway. And then, here's the example of the model itself. So there are a couple restrictions with model definitions that come to SambaFlow. The first is that modules with parameters have to be defined before the forward, right? So you can't define more of your model after your forward, or in your forward, actually, even. And the return type of the forward should be simple. So it should either be just a tensor or maybe a tuple or list of tensors. Something that is easily consumed. And that is this is, as you can see, pure torch mostly. There's no real, nothing in here that would strike you as SambaFlow. There is one difference. One thing that you can do with an RDU that you really can't do with a GPU. And if you look at forward, you look at the line just above the return, you'll see that we're actually defining the loss as part of our forward function. So because of the way SambaNova compiles and builds pipelines in RDU, your optimizer, your loss function, can be a part of your graph. There's no need to leave the cycle, compute loss, and come back. It's all one pass. Forward, backward, optimizer, gradients are all part of the same loop on the same chip. So you can include your loss here, which greatly improves your performance because you leave chip less. You stay on the RDU, so you get that maximum throughput. And then the tracing, here's a little example of it. So as I mentioned earlier, if the Samba tensor goes through a torch function or module, then it will be traced and automatically converted for Samba operations. So you'll see here, for example, a module, comp2d. When you pass in a Samba tensor to that module, well, the tracing will end up calling SambaFlow version of comp2d rather than the torch version. So there's no need for you to explicitly convert there. You just feed it a Samba tensor and it will trace it for you. And it does the same thing, not just for modules, but also for functions. So for example, we're calling ReLU on a Samba tensor. That will automatically be pushed to the SambaFlow version of ReLU and give you back the result. As mentioned in the thread, is that these are all listed as part of our docs. So if you go to docs.SambaNova AI and go to the Samba APIs, all the functions that we support are listed there. So that includes torch modules, torch functions, and tensor functions. Okay, and now to running your model. So you've compiled it, you've traced it, you're ready to go. You have your PEF. So the run facility is samba.session.run. You call that function. So you provide all the input tensors. So that will actually be your data, right, that you're going to train on. And you provide the output tensors. So the output tensors are what you got from the previous tracing, right? So when you trace the model, it'll actually flow those dummy tensors through the graph, and it will output tensors at the end. And these tensors will be the shape that the model expects and what SambaFlow will look for. So you provide those two things, and then you provide something called section types. So I mentioned things like forward, backward, optimizer, gradient, normalization. Those are all individual sections. And by default, they're all pipelined together, one after the other, and they loop automatically. You can run them one by one, right? So you can split up your running as you need to. And we'll talk about that in a little bit. So you call your run, and that will give you outputs. And the output of that run will be the output of your forward function. So that will be your loss, your logits, whatever it is that your forward function outputs. You can take those and you can then, feed them forward so that it keeps training, or you could capture them and push them to the CPU for further analysis. If you want to track how your model is performing over time, you could take your loss values and output them so that you can, review them. Or you can pull out individual gradients from your model. For example, here, we're calling the SN grad of the weight of the first linear layer. Okay, and of course, this lets you sync between CPU and RDU, because SambaFlow doesn't yet support everything that PyTorch does. So there will be times where you have to run a function on CPU. For example, we don't support every loss function. So you might have to sometimes do loss off RDU and do it on CPU. Okay, and that's when you would do that syncing. Okay, and just as another example, if you just want to do inference, say you already have a trained model, then if you want to run inference, well, you just need the forward section, right? And then you just feed in your your evaluation data or your real data, and the output of the run will be the prediction. Okay, and this is an example of a partial model run on RDU. This is usually the case when you have a loss function that we don't support directly in SambaFlow. So what would happen is you would run you'll run just the forward section. So you in your run command, you would say section type forward, and you would capture the output. In this case, we're capturing the first element because that's the actual loss that we want for this particular function. We would then say to Torch to take those Samba tensors and convert them back to Torch tensors. Then, since we're going to be running on host again, and we're going to be running the training loop on PyTorch now, we'd set requires grad to be true. Right now, we're working in PyTorch. You'd call your criterion, your loss function, on those partial outputs with your targets. You call backward, so you do the back. So you call the back prop. And now that you have that back prop, you have the backwards gradients. You then call run again. This time with the grad of the outputs. So you convert those to back to Samba tensors, your loss functions, and then you'd run the remainder of the graph. So you'd run the backward with those new gradients, and then you run optimization on RDU. So while this is less than ideal, right? You want to stay in RDU as much as possible for maximum performance. You can go to RDU. You can go back to CPU to do additional work that we might not support yet in SambaFlow. Okay. And just to reiterate, you would usually do this when SambaFlow itself does not support your loss function. So, for example, we support things like AtomW, SGD, those optimizers. If you're not using one of those, then you could move over to CPU to do that. So that's the most common use case for moving off of RDU. Okay, So a little bit more detail about session.run. So it's often the case that as you're running the model can expect changing parameters during runtime, right? Oftentimes this is like, learning rate schedules, maybe weight decay, dropout rates, momentum. Those are things that often change during runtime. Well, we can support that. So we have a dictionary called hyperparam_dict. And what you would do is that so for those values you expect to change on a schedule, you would put them in this dict, and then you would pass that dictionary into session.run. And then as those values change, we would feed them into the model automatically as part of the run. So you're not locked. You can apply your typical schedules to your models when training on RDU via this method. And then we provide some functionality for measuring performance on RDU. So we can measure performance of a full model, so the entire graph, or just per section. So we can just measure the backward portion if you feel that's the problem, or just the optimizer. And measure performance that does the entire graph. The key input to it is run graph only. So when you do this, what you're going to get is what we call the roof line. So that's the maximum theoretical performance of the RDU if everything was perfect for this model. It's not, so it doesn't run it with the real data. And then measure sections. Well, that's when you provide the section you want to run. So you want to run forward and backward, then this is what you would use for that. And then you'll get your throughput and latency for your model at its theoretical peak performance. So it lets you know, sort of the maximum you can achieve with your current model structure. Okay, and then so some examples of how to compile and run, and some arguments. So we use argins to help control the various aspects of the model. So for example, inference. So that's a Boolean flag. So are you running this model inference or not? For example, batch size and batch size. And batch size really does matter. So does micro batch size. Because when those values change, you actually have to recompile the PEF. Because remember, I said that you have to trace the graph, that the compiler has to know the shape of your tensors to effectively map onto RDU. Well, if you compile for a specific batch size, say 32, then the graph that gets built onto RDU will expect an initial input of 32 tensors. So it will map that onto chip. So if you try to give it so if you then say run the model with a batch size of 64, it'll get an error because the compiler will say, wait a minute, you only built this for 32. 64 won't fit onto the chip in this structure. So you want to watch for that. Batch size is one of those things that if you change it for the model, you need to recompile. And here's an example, compile command. So just Python, your application's name, the compile flag, and then the input parameters. And this is how it gets broken down. So we use we use the implementation of the arc parser. So we built ours on top of the Python arc parse. So we pull in the args command, compile, pull in the batch size, micro batch, and the inference. And then we have the run command, which is basically the same. All you're really changing is the fact you're saying run now. And that's where that if then statement I showed you earlier in a main function. And now some sort of best practices. So your inputs should be well defined, which also means the internal tensors in the model. The compiler has to see every symbol in order to effectively and optimally map the graph onto chip. This usually isn't too hard to know. If you're familiar with your model and your data, then you know what the inputs will look like. So you just make dummy tensors on that shape. Try to contain your operations to one continuous graph. So as much as possible, don't go to CPU, right? You want to keep it all in RDU to get your maximum performance. No control flow. So again, if your model has an if then else in the forward, we'll only follow the true path. We won't ever follow, we won't even see the false branch. And in the vein of keeping your graph continuous, so try to limit your synchronization between CPU and RDU. There is, of course, an overhead. And for larger models, with lots of operations, that could result in thousands to hundreds of thousands of calls between RDU and CPU, and that will just completely destroy your performance. And something that I hope that you got from this is stick with PyTorch. You really only need a few explicit commands from SambaFlow to have your model working in our environment. So keep your code PyTorch, add in those few calls from SambaFlow, so like the from torch model underscore and from torch tensor, and you'll be good. So that was a lot of information. So just want to check if there's any questions or anything that you want to comment on, anybody? Okay. So dynamic graphs. I don't believe we have support for that yet. And did I hear a voice?
Yeah, quick question. If you wanted to train on SambaNova system and then say offload.
You're kind of quiet. Could you please speak up?
Yeah, if we wanted to train a model on SambaNova system and then offload our weights, maybe publish it in a Hugging Face or something, are there functions that can translate the weights into something more usable for its general CPU inference?
Sure. At any point, you can always call toCPU on your weights, and they will be exported into torch tensors. So when you convert from RDU to CPU, we will output torch tensors for you, and then you can take those and do whatever you wish with them. So you can checkpoint them, you can feed them into a CPU or GPU. They're just raw, weights. You might have to make considerations for data type. So for example, our default internally to the RDU is bfloat 16. So you might have to do a conversion to like floating point 32 if you want to use that. But in general, you can just toCPU on the RDU, and it will just give you back your torch tensors that you originally had, and you're free to use them as you wish.
Thank you.
No problem. Any other verbal questions? Okay, so there's one last little extra thing I want to share, and that's the Samba loader. So you've seen that we provide methods for handling torch tensors, right? The Samba tensor. Well, we also have a means to enhance and improve the torch data loader. So the Samba loader is just a wrapper around the data loader from Torch. And what it does is it more efficiently parallelizes load ops and graph ops for use on RDU. So it better interleaves those things. And as a bonus, you don't have to explicitly convert your tensors into Samba tensors. The Samba loader will do it for you. So what it gives you back, much like the Torch data loader does, is it gives you an iterator over your Samba tensors. And so whenever you call the Samba loader function, you'll get back a Samba tensor automatically. So you don't have to call the from torch tensor when you use this particular function. And here's what that would look like. So Samba loader, you give it the torch loader, which is an iterable. You give it a list of names, right? Because Samba tensors are named. So you want to give a list of names for each of the tensors you expect from the data loader. Okay, and then here's an example. So you import your data loader from Torch, you import the Samba loader from SambaFlow, define your data loader, and then you just wrap your Samba loader around that data loader. And then you can just loop over the Samba loader, and it's an iterator. So it just gives you back Samba tensors for each call. Really simple, really neat, and it can help improve performance of your model, because the Samba loader is built for the RDU, so it knows how to optimally map load ops with graph ops. And as a final note, much like the Torch data loader, SambaLoader supports pin memory. So you can pin pages in memory for faster access. Okay, so that's in a nutshell how to use SambaFlow and how to bring your model from Torch to our platform. Hopefully that was clear. If not, please feel free to ask. But yeah, thank you all for your time. Appreciate it.